What's up there, boys and girls and everyone else? Welcome to another science video lesson, and in this video lesson we will going to talk about derivation of mirror formula and magnification. So what is that all about? So stay a while guys and listen as I discuss this one here in our video lesson. So what are you waiting for? Let's go now. Alright, so here we are in our video lesson topic for today. So mirror formula and magnification derivation using ray diagram. That's right guys, so we will going to use ray diagram for our topic that we have right here. So what is a ray diagram? So you can watch that video lesson here on the link above. So just click the link above to watch again that video lesson about ray diagram. Alright, so what is mirror formula and magnification? Now the ray diagram is a qualitative approach. Okay, it is a qualitative analysis on how the image will look like and where is it located. That is a qualitative approach. Now, in this particular topic that we have here, we will going to use a quantitative approach. Alright, we will use the quantitative approach to identify the characteristic of the image using numbers. Alright, using numbers. But before we go to that, we need to use the ray diagram in order to find out this mirror formula and magnification that we have here today. Alright, so since we have encountered already different kinds of mirrors, so spherical mirrors, and we have also lenses that we have. Alright, so we have two mirrors that we have encountered before. That is the concave mirror and then the convex mirror. So what is the mirror that we will going to use in this topic? So obviously the more straight to the point, okay, ray diagram that we have is the concave mirror. Okay, so we will use the concave mirror in this topic that we have so that we will be able to easily identify the mirror formula and magnification, all right, in the process. So let's start now. Alright, so in a typical ray diagram, like the one that we have right here, the concave mirror, first we have here the principal axis, okay, drawn at the center of the mirror, and we have 2 points. Alright, so we have the 2 points, we called it the center of curvature and focus. Alright, so here's your object, okay, that we have right here. This is the object, and we have here the first ray. Okay, so the first ray that we have is the principal ray. So the principal ray goes to the principal axis parallel to it, and it goes to the focal point. Okay, next one is the focal ray. The focal ray is a light ray that goes to the focal point down to the parallel to the principal axis. Alright, so focal point to the principal axis. So F to P. Alright, so in a typical ray diagram, we can be able to, we can able to identify the characteristics of the image using the ray diagram itself. So in this case, the image is reduced, and at the same time, it is alright, so it is inverted. Okay, so it is inverted. This is a real image that we have right here. Now the question is, okay, so the question is, in a typical mirror problems, alright, so in a typical mirror problems that uses numbers, what are the things that we can use? Okay, so what are the things that we can use? So in this case, I forgot to tell you about the center of the mirror, which is called the pole. Okay, which is called the pole itself. Alright, so going back to the question, how will we going to solve problems related to mirror if it is in a number, if there are numbers, okay, if there are numbers on it. Okay, so can we possibly identify the characteristics of image not only by ray diagram but also by quantitative means? Okay, so these are the formulas that we will going to use in this mirror equation. Okay, so in this discussion that we have, okay, so in this discussion that we have, we will try to find out where does this equation came from. Alright, so where this equation came from. that we have right here. Okay, I will not only discuss in this video lesson where what is the formula all about. I will also discuss where the formula came from. All right, so how it came to be. Okay, using the ray diagram that we have right here. Okay, so let's derive now. Okay, let's go now to the idea of the mirror formula. Okay, so this is our mirror formula over here. Okay, so as you can see, the mirror formula has a lot of letters on it and has a lot of, since these letters represents the variables. Alright, so what are these variables? What are these variables all about in this formula? Okay, so these variables talks about distances. These variables talks about distances. So the first thing that we have right here, we will put some points on the mirror. So the first one is the pole of the mirror. And I have another one here, the point A, which is the position or the place where the object is located. Alright, so, and this one. Okay, so let's take a look at point A and point P. Alright, so the distance between point A and point P is called the d sub O. Alright, so that is the d sub O, or the distance of the object. Alright, so that point A and point P is the distance of the object and the mirror. Alright, so that's the first one. The next one is this point. So the location of the image, I called it point R. And I will just continue up the line there. So together with this tangent line over here, so what is this distance between these 2 points, the R and P? What is this distance between these 2 points? So we called it d sub I, or the distance of the image and the mirror. Okay, so that is the distance of the image and then the mirror, or we called it d sub I. Alright, finally we have these 2 points. So we have F and P. Alright, so we have this F and P points. Alright, so what does this one represents? This one represents the focal length. Alright, so this one represents the focal length. And what is this focal length all about? The focal length is the distance from the focal point and the pole of the mirror. Alright, so distance from the focal point and the pole of the mirror. Now, what is common among these three? Aside from they are talking about distance, okay, these three is talking about distance, they also have one reference point. Alright, so it also has one reference point. The distance that you have right here talks on one reference point only. And that is the pole of the mirror. Alright, and that is the pole of the mirror that you have over there. Okay, so that is the distance that we are talking about here, the reference point. Okay, as you can see, we are not talking about any points in space. Only by the pole in your mirror. Alright, this is the reference point. So, with that, the question is, if we change the position of the object, right here, okay, is it possible to make the formula change as well? Alright, so if we change the mirror, alright, so if we change the mirror that you have right here, if we change the mirror to convex mirror, is it possible for the formula to change? Alright, so the answer to both questions is no. It's because this formula that you have right here, this mirror formula, doesn't depend on the position of the object. Besides, the formula is talking about distances only. Alright, it talks about the distances. None of the variable on your formula talks about the position of the object. Next one, it doesn't depend on the mirror that is used. Whether it is a concave mirror or a convex mirror, whether it is a concave or convex mirror, it doesn't matter. It is the same formula. The formula doesn't discriminate what mirror are you going to use, and it is only not a. It is this formula is not only available for one mirror, one kind of mirror, but also the other kind of mirror. All right, so convex and concave alike. Okay, so we all know that the distance. Okay, we all know that this formula is all about the distances, all right, of the object to the pole, all right, the object, the image, and the focal length to the pole of the mirror. The question is, where does this formula came from? All right, where this formula came from in the first place. All right, so to answer that, we need to recall some basic math concepts, especially in geometry. We call it similar triangles. We all know that similar triangles are triangles with the shape, same shape. Okay, to call it a similar triangle, two triangles must have a same shape. All right, so we have the same shape. Okay, so as what you can see right here. Okay, we can say that these two triangles that you have right here are similar to each other. Because if you take a closer look, triangle ABC is similar to triangle DEF. Alright? So, although this is only a scaled down version of ABC, okay, triangle DEF is just a scaled down version. They have the same shape, so therefore we can call it a similar triangle. So what are the ways that we can use in order to prove that these triangles are the same? So what are the ways that we can use in order to prove that these triangles are the same? The first one is by angle. Alright, so by looking at the angle of this triangle, we can prove that these triangles are the same. Example, we have angle A and angle D is the same. Okay, so they are congruent to each other. Alright, next one. Angle B is also congruent to angle E. And finally, we have angle C is congruent to angle F. So therefore, all three angles on your triangles, okay, all three angles found in these triangles are similar to each other. So if they are similar to each other, also with this is the angle, also with their sides. Their corresponding sides. Alright, so we have here the side AC is similar to side DF. Alright, and also we have side AB is also similar with side DE. Also with side BC is similar to side EF. Okay, so there you go. Okay, also with their side. Now, with the proof that we have their angle and their sides congruent to each other, we can say that these two triangles pass the AA similarity test for triangles. Right? So, these two triangles that we have right here passed the AA similarity test. So, we can say that these two triangles are similar to each other. Alright. Now, since we recalled now what is similar triangles is all about, we can use the concept behind these similar triangles. We can use this concept to figure out how to find the mirror formula. Alright, so let's move on. Alright, so this is now the mirror formula that we have right here. Okay, so now I will add some points. All right, so I will add some points in our diagram, okay, for us to better visualize what is happening. All right, so we have I added okay, point L, which is the top of the object, point I, which is the top of the image, and point X, this is the point that is tangent to the mirror. All right, so where the focal ray touches down. All right, so on point X, we have I have also point D. This is also tangent to the surface of the mirror. Okay, so these are tangent to this is tangent to the surface of the mirror, and this is where your principal ray touches down. Okay, in the surface of the mirror. Okay, so that is point D. All right, so in this case, we will try to find out how many similar triangles do we have right here. All right, okay, so how many pairs? So we have 1 over here. So we have 2, we have 3, and we have 4. Okay, so all in all, we have 4 pairs of similar triangles that we have right here. But we will not use all 4. We will just extract it into 2. Alright, 2 triangles, similar triangles, 2 pairs of similar triangles only. Alright, so in this case, we will going to use this triangle over here. and the triangle over there. Okay, so that is triangle LAF. Alright, so that is triangle LAF, and we have triangle XPF. Alright, so there you go. So, according to our judgment here, these two triangles are similar to each other. Now, let's prove that they are similar to each other. So the first proof is the angle between the right angles that you see here. These right angles that you see here. Okay, so according to this proof, that this claim that angle LAF is similar to angle XPF. Now, what is the reason why they are similar? Because both of them are 90 degrees. Okay, so both of them are right angles. Alright, next one. We have another one here. Alright, so we have another one here. These are vertical angles. Okay, so we have here the vertical angles. So angle, okay, so angle AFL, all right, is similar to angle XFP or PFX. So PFX. All right, so what is the reason why they are similar? Because they are vertically opposite. Since there is an intersecting line, okay, on that particular area, so we can say that they are only vertically opposite, but they have the same angle as well. So we call it vertical angles. All right, vertical angles are equal. All right, so next one. How about this angle over here? Okay, so angle over there. So we called it angle ALF. ALF is congruent to angle PXF. All right. So do we even need? All right. So do we even need to prove this one? Okay. Maybe we shouldn't need to prove this one, because if these two pass the okay, if these two prove that these two triangles are similar to each other, then logically speaking, this claim can be also proven. These angles that you have right here, we can say that they are the same with each other. Okay, they are the same with each other. So we can say that these two triangles, triangle LAF and triangle XPF, are similar triangles based on the AA similarity test. Alright, so similarity test. So they are similar triangles. Alright, so since we know that these two triangles are similar to each other, we can use now their sides. Okay, we can use now their sides to find out how we can use that in deriving the mirror formula that you saw earlier. Alright, so again, we will put some points over here. Okay, so let's use the sides that we have right there. So again, triangle LAF is similar to triangle XPF. Alright, so let's use the side. So this side that you have right here. Okay, so we have AL. Right, so we have AL. And we have PX. Alright, so PX. Then next one, we have this side. Alright, so we have this side. We have AF. What side is congruent to the other triangle? So we have PF. Next is we have the LF. And we have the XF. Okay, so we have LF and we have the XF. Now, we don't need the LF and XF this side. We don't need this side anymore. There's no much use about that one. So we only need these two sides that you have right here. All right. So what does each side represent? So let's start with this one. So AL represents the object. All right. So AL represents the object, and AL is the height of the object. Alright, so that is the height of the object. So we called it h sub o. Alright, next one. How about the px? So px, if we will trace this px down here, so this is the image. Okay, so this is the image. So we can say that px is the height of the image. Alright, so that is the height of the image. Now, how about the AF and PF? Now, if you take a closer look, alright, so if you take a closer look, AF and PF is under AP. AP is the total distance. We called it D sub O. Alright, or distance of the object from the mirror. So, we get AP, okay, we get AP by adding AF plus PF. Alright, so we get AP by adding AF and PF. So, what does AP means? So, we have it right here. So, we have AP means D sub O. Then, we have PF. So, earlier, we knew that PF represents the focal length. Okay, so that is the focal length. Alright, so what about AF? Okay, so in order to get the AF, we should derive. Okay, we should derive coming out of this formula. So we can get AF as D sub O minus F over F. Okay, so we have now our first formula over here, or first equation needed to find out the mirror formula. Okay, so that is for the triangle LAF and triangle XPF. Okay, so let's go now to the second equation. Okay, so for the second equation, let's put again some points. Okay, so let's find out more triangles or more similar triangles that we have right here that is similar to the previous one. Okay, so we can use this triangle over here. Alright, so we can use these triangles over here. So we called it triangle IRF, similar to triangle DPF. Okay, so do we need to prove this one? Okay, it has a right angle over here. Both of them have right angles and both of them have vertical angles over here. Both of them have vertical angles. So therefore, okay, so therefore by double A similarity test, we can say that these two triangles are similar to each other. So therefore, we can proceed now using their sides to find out the second equation. Alright, so what are those sides that we have right here? Okay, so we have here the DP. Okay, PD. Right, so we have PD over RI. Is equal to, we have RF. Okay, RF. And we have PF. Also, we have IF over here, right? So we have IF and we have DF. All right. Again, we have not much of a use of this side. Okay, we do not have any use of this side, so we can cancel that one out. All right. So let's start first with PD. PD, if we were going to trace PD over here, this is the object. This is again your object, and PD talks about the height of the object. Alright, so we can write it down here, the height of the object. Next one, how about the RI? Alright, so how about the RI? The RI is the height of the image. So again, this is your image. So it can be we can say that this is the height of the image. Alright, so how about RF and PF? Now, RF and PF lies on RP. Okay, so RP. We can say that the RP is the total distance of the image to the mirror. Alright, so that is the total distance of the image of to the mirror. So we can get RP by adding RF is equal, or RF plus PF, respectively. Alright, now, we all know that PF, you all know that PF is your focal length. Alright, so focal length, that is your PF. Now, what about RP? Alright, so what about RP? So if you take a closer look about RP, so you have encountered this one earlier. So this is the distance of the image to the pole of the mirror. Alright, so that is the distance of the image to the pole of the mirror. So we called it d sub I. Okay, so there you have it. So how do you find out the RF? So how do you find the RF? So you just derive, okay, you just transpose this RF, okay, you just transpose everything here to get d sub I minus f over f. Okay, so d sub I minus f over f. So this will be our second equation. Now that we have our second equation, we are now good and ready to go to find out the mirror formula. Alright, so that was for the triangle IRF and triangle DPF. Okay. Now we are now ready to derive the mirror formula. So number one, the first equation that we have encountered earlier, so we have h sub I is equal to d sub O minus f over f. Alright, so the second equation that we have earlier, which is the h sub O over h sub I, is equal to d sub I minus f over f. Alright, so we need the third equation. The third equation doesn't require a diagram anymore. Okay, so the third equation, what we need to do on the third equation is, we will just do the inverse of this equation number 2. Alright, so we will just do the inverse of equation number 2. So what will happen? It will become h sub I over h sub O is equal to f over d sub I minus f. Alright, so since this one is the inverse of this, so we don't need this one anymore. Alright, now take a closer look. Take a closer look on our formula. Now, what else can we cancel? Okay, what else can we cancel here in order for us to easily find out the mirror formula? So we can cancel the height of the image and height of the object respectively. So we can cancel this one out and come up with this formula. So rather, okay, f tapo and we have, yeah. Alright, so we have now this formula, then cross multiply. So f squared is equal to d sub I minus f times d sub O minus f. Alright, so doing the basic algebra. Alright, so let's do the basic algebra here. So f squared is equal to d sub I, d sub O minus d sub I f minus d sub O f. Alright, and plus f squared. Okay, so we can cancel the f squared. Okay, we can cancel the f squared and transpose this one over here. Alright, so transpose this formula over here to make it d sub I, d sub O is equal to d sub I f plus d sub O f. Alright, so what is the final thing that we need to do in order to find out the mirror formula? Okay, in the process. So we will divide both sides by, right? So we will divide both sides by d sub I, d sub O f, and we have d sub I, d sub O f, then d sub I, d sub O f. Right, so we will divide both sides by those variables. And we can cancel now similar terms. Okay, so what is left behind is f here. Then cancel d sub I, and also with the f, d sub O remain. Next one, d sub O, and also the f, d sub I remains. Alright, so finally, our formula that we get in the process is the mirror formula over here. Alright, so that is the mirror formula over there. That is the mirror formula, or that is the equation that you're going to use whenever you encountered problems related to mirrors, whether it is a concave or a convex mirror respectively. And what is the most amazing part here is this formula came from a ray diagram. Alright? This formula that we have right here came from the ray diagram. Okay, so let's go now to the magnification formula. Alright, so with the magnification formula, we are very fortunate that the magnification formula is just the ratio. Alright? It is just the ratio of what? It is just the ratio of two different variables that we have right here. Mainly, we have the distance of the image to the object. That's the ratio between them. And also, the height of the image and the height of the object. Okay, the ratio between the two. Alright, so if you will notice, this triangle over here, alright, so this triangle over here and triangle over here, okay, has different size. It has different size. So the ratio of their sizes is related to the term called magnification. Alright, so magnification is the ratio between height of the image and height of the object. Also, the distance of the image and the distance of the object. Alright, so let's take a closer look about this on that one. Okay, so if you take a closer look, you will see that Ri and Al are in ratio with each other. So therefore, we can have it Hi over Ho. So we can use this one as a part of your magnification part of the magnification equation. Alright, now as you can see here, that your image is inverted. Okay, in a Cartesian plane, alright, the sign that is below the Cartesian plane is negative. So therefore, if it is inverted, okay, negative means inverted. Okay, negative means inverted. So we can say that the magnification of this image is negative. Alright, so that the magnification of this image is negative. Next one. We have here the xi. Alright, and we have the AP. Xi represents the distance of the image, and your AP is distance of the object. Again, we can use this one. Alright, we can use this one to find out the magnification of your image. We can use this one to find out the magnification of the image. So, ratio of the distance of the image over the object, relative to the object. So again, by sign convention, alright, so by sign convention, the object is, or the image is inverted, so therefore we have negative magnification over here. So, if you transfer that negative, alright, so if you transfer this negative over to the other side, alright, so if you transfer that negative over to the other side, we can get the final equation here, alright, so we can get the final equation here. Magnification is equal to height of the image over height of the object is also equal to negative distance of the image over distance of the object. Alright, so how does the formula work? You can compute the magnification using this one. Also, you can compute the magnification by just only using the distance. Or, you can use this 4 terms. You can use these 4 terms to find the missing term. Okay, that we have right here. For example, your distance of the object is missing. Distance of the object is missing. But what is given is the height of the image, height of the object, and distance of the image. Now, in order to get the distance of the object, you can use this formula. Okay, if this three is given. Okay, so that was your magnification formula. All right, so what we learned today right here. First is the magnification formula. Magnification formula is just the ratio. Okay, that's just the ratio between the height of the image and the distance of the image to its relative to the object. Okay, so magnification formula. And finally, what we have right here is the mirror formula coming out from ray diagram. It says that 1 over the focal length is equal to 1 over the distance of the object plus 1 over the distance of the image from the mirror. Alright, so these are the two formulas that we will going to use in our analysis with regards to quantitative approach in the characteristics of the image produced by concave and convex mirror. Alright, so with that, okay, so we just ended up another science video, everyone. So if you learned something about this lesson that we have right here, if you learned some values or some concepts about this lesson, just hit the like button on this video. It's down there. Okay, it is okay, you can freely click that one. Okay, next one is to subscribe to my channel. So it is right there. So subscribe to my channel for more science video lesson and updates. Okay, so the notification bell for more updates about this lesson that we have right here, the video lesson in the future. So if you have question and comments, you can write it down in the comment section below this video. So it will help me a lot. Alright, so that ends up our video lesson, okay, for today. So I hope you did learn a lot, guys, from this one, and let's see each other next time. Peace out. Peace out, guys. Peace out. Okay.
Bakaみたい子供なのね夢を追って傷ついて嘘が下手なくせ